In the previous lesson, we learned how to use the stoichiometry flowchart right here, and how we always start from our given on size A, and we solve for any unknown unit on the flowchart. This is where we end, and the given is where we start. And the path we're going to take is basically multiplied by the conversion factor. And we learned that some of the conversion factor are incomplete. For instance, the molar mass, the number of grams, is based on the chemical formula of that substance. In this case, we are going to look at another conversion factor that allows us to connect A and B, because so far we only focus on this side only. What about side B? That is this right here. This conversion factor allows you to connect between chemical A and chemical B. This is called a mole ratio. So this mole ratio is basically allow us to connect between chemical A and chemical B. Now, where do we get this number from? This number is coming from the coefficient number of a chemical equation or the subscript number of a chemical formula. But before we look at those specifically, in this lesson we are going to look at specifically the number coefficient and how we can look at the chemical equation to determine the mole ratio of between A and B. First of all, when we look for the mole ratio conversion factor, a mole ratio is a conversion factor from a balanced chemical equation. Again, it has to be a balanced chemical equation. Notice how we have a balanced chemical equation here. What does the word balance mean? The word balance means that the number of atoms on this side must equal to the number of atoms on that side. For instance, we have one carbon atom. This side also have a carbon atom as well. We have 4 oxygen. This side also have 4 oxygen as well. That's why we have the term balance. The beautiful part about this is that most of the chemical equations given to us are balanced. So here we have a balanced chemical equation where we have CH4 plus 2O2 produce CO2 plus water and 810 kilojoules. We call this side the reactant. We learned that before. The reactant is the starting materials of a chemical reaction, and the starting material will produce the product, and the product is the ending materials or the result that we produce in the process. In this case, we are going to focus on getting the mole ratio, and to do that we focus on the coefficient number. And what is the coefficient number? That is the number in front of a chemical formula. So this is a coefficient number. In this case, let's look at this chemical equation. We don't have a number in front of CH4, so we assume it's going to be 1. So we have 1 mole of CH4 react with 2 moles of oxygen. Notice how I use a mole, because if you notice, based on the stoichiometry flowchart, the unit mole allows us to convert from one unit of chemical from one chemical to another chemical, as well as can branch off to a different unit. That's the reason why we use a unit mole as our main unit when we count the substance in a chemical equation. So let's go back. Again, we have 1 mole of CH4 react with or plus 2 moles of oxygen, produce in the product side 1 mole of CO2 and 2 moles of H2O, which is water. Given this balanced chemical equation, we can write many conversion factors. For instance, find the mole ratio between multiple problem here, right? Here are the multiple set of conversion factor between CH4 and kilojoule. Kilojoule is a unit of energy. So every time you see kilojoule, which is represented by kJ, you know it is energy. So CH4, what's the number in front of CH4? We know it's 1. And kilojoule, what's kilojoule? It's a unit of energy, so we're looking for kilojoule right here. Give us the unit of energy. So we have 1 mole of CH4 because the coefficient is 1. So 1 mole CH4 equal to kilojoule, which in this case is 810 kilojoule. And this is our conversion factor. Based on this chemical equation, let's try another one. Look for the conversion factor or the mole ratio between O2 and energy. This is O2 right there. And energy again is a unit in kilojoule. So we have O2, which is 2 because of that coefficient there. So we have 2 mole of O2 equal to energy. And we have energy measured in the unit of kilojoule. So we have 810 kilojoule. And that's it. Let's try another problem right here. We have CO2 and water. Carbon dioxide, which is CO2, is right here. There's no number in front of it. We assume it's going to be 1. So we have 1 mole of CO2 equal to how many moles of water? Or H2O right there. That number 2 give us 2 mole of H2O. And if we look back at the problem, this can be represented by pictures like 1 mole of CH4, 2 moles of O2, 1 moles of CO2, and 2 moles of water. Lastly, we have energy. Let's look at another chemical equation. Here we have C3H8, which is propane. If you ever go camping, this is the gas that you burn to cook when you go camping. And propane reacts with 5 moles of oxygen. As you can see, there are 5 of those right here. And this produces 3 moles of carbon dioxide. Notice how it 3 moles of carbon dioxide and 4 moles of water. Lastly, we have energy. So again, this side of the chemical equation is called the reactant. And on this side of the chemical equation is called the product. And the reactant are the starting material, the product are the ending materials. Our job is to find the mole ratio between based on the condition that's given to us. Here we have C3H8 and kilojoule. Again, kilojoule is another unit for energy. So we assume that it is energy. In this case, there's no number in front of C3H8. We assume the coefficient is going to be 1. So we have 1 mole of C3H8. And for kilojoule is a unit of energy, which is right here. We have 2,220 kilojoule. Then the next problem we have O2 and energy. Again, energy is measured in kilojoule. So for oxygen we have 5 moles of O2. And for energy is 2,220 kilojoule. And lastly we have CO2 and oxygen. For CO2 we have a 3. That tells you there are 3 moles of CO2. And for oxygen, the coefficient is 5, so we have 5 moles of O2. And again, that's how easy this problem can get.